Did you know that the CPU inside your computer can hold over 90 billion transistors, each smaller than a virus particle, yet powerful enough to execute billions of calculations every second? The CPU, often called the brain of the computer, processes instructions, performs calculations, and manages nearly all data flow within a system. What's even more mind-blowing is that a single chip, smaller than your fingernail, is now more powerful than the massive supercomputers that first helped land astronauts on the moon. Today we'll dive deep into the incredible world of CPU technology and uncover the hidden process behind how these tiny yet mighty chips are made. From spotless clean rooms larger than football fields to microscopic transistors thousands of times smaller than a strand of hair, the journey of a CPU is nothing short of extraordinary. The story begins in 1971, when Intel introduced the world's first microprocessor, the Intel 4004. This invention paved the way for smaller, more powerful computers. Soon after came the Intel 8086, the processor that powered IBM's first personal computer in 1981, changing the course of history. Through the 1980s, Intel kept pushing forward with the 80286 and 80386, improving speed and multitasking. By the 1990s, the Pentium processor was born, fueling a revolution in computing power and multimedia capabilities. At the same time, IBM joined forces with Motorola and Apple to create the PowerPC architecture, trying to break Intel's dominance. And while IBM eventually shifted away from consumer PCs, Intel kept driving CPU innovation with its Core series, powering everything from desktops to servers and data centers. The CPU creation process begins with sand. Yes, sand. More specifically, quartz, which contains silicon, the base material for chips. This quartz is refined into silicon with 99.99999% purity, a standard called 9 nines purity. The purified silicon is melted and carefully grown into a cylindrical crystal called an ingot, which can weigh over 100 kilograms. These ingots are then sliced into ultra-thin wafers, each thinner than a credit card but worth up to $100,000 after processing. Once wafers are ready, engineers coat them with photoresist, a light-sensitive chemical, using ultraviolet light and stencils called photomasks. Microscopic circuit patterns are imprinted onto the wafer. Each photomask costs around $300,000, and the process is repeated up to 80 times per chip. These patterns are unimaginably small, just a few nanometers across, thousands of times thinner than a human hair. The etched patterns are then filled with layers of copper and insulating materials, building the complex wiring that connects billions of transistors. Each layer is thinner than a sheet of paper, and the wafer goes through this layering process nearly 80 times, amounting to more than 900 individual steps. At every stage, precision is critical. Just one speck of dust can destroy an entire chip. That's why clean rooms in these factories are more sterile than hospital operating theaters. Next comes ion implantation, where atoms like boron or phosphorus are fired into the silicon at extreme speeds to alter its electrical properties and form transistor channels. Imagine firing baseballs into concrete walls. That's the kind of force used to implant atoms into silicon. To repair the crystal structure afterward, wafers are heated to around 1000 degrees Celsius in a process called annealing. When manufacturing is complete, wafers are tested with powerful electron microscopes and advanced metrology tools. Even the slightest defect is detected, and not all chips make the cut. The working chips are then categorized or binned into product lines such as Core i9, i7, or i5, depending on performance. After testing, lasers slice the wafer into hundreds of tiny CPUs. Each one is mounted onto an interposer, connected to larger circuits, and topped with a protective metal cover called a heat spreader, which keeps the CPU cool. Before leaving the factory, every single CPU undergoes rigorous stress testing to ensure stability and performance under heavy workloads. But CPUs are just one piece of the larger microchip industry. To understand their full story, we must also look at the three biggest players: Intel, TSMC, and ASML. Intel, founded in 1968 by Robert Noyce and Gordon Moore, pioneered microprocessors and continues to power everything from personal computers to massive data centers. TSMC, founded in 1987 by Morris Chang, revolutionized the industry by focusing solely on manufacturing chips for other companies, allowing giants like Apple, Nvidia, and AMD to thrive. Then there's ASML, founded in 1984 in the Netherlands, which became the world's leading supplier of lithography machines. ASML is the only company capable of producing EUV lithography technology, an advanced process using extremely short wavelengths of light to etch the tiniest circuits ever made. The microchip revolution begins with silicon wafers, but the designs are crafted digitally. Engineers use advanced software to create layouts for billions of transistors, optimizing them for speed and energy efficiency. Since the patterns are far too small to draw physically, photomasks are created, high-precision glass plates, etched with the blueprint of the chip. These masks guide the lithography process, projecting the intricate designs onto the wafers. The result? A microchip so small you can hold it between your fingers, yet powerful enough to drive smartphones, laptops, data centers, cars, and even spacecraft. With each generation, chips become faster, more energy efficient, and more powerful, shaping the future of technology in ways we can barely imagine. Modern microchips are marvels of engineering, built through a process so precise that it borders on science fiction. These chips use a technique called extreme ultraviolet lithography, or EUV, which can print features as small as 2 to 5 nanometers. To put that into perspective, that's over 10,000 times thinner than a single human hair. This microscopic precision is what allows billions of transistors to be packed onto a single chip, powering everything from smartphones to supercomputers. At the heart of this process is the photomask, a tool that reduces complex circuit designs to an atomic-level scale. Since microchips are made up of multiple layers, each containing specific parts of the circuit, like logic gates, memory cells, and electrical connections, multiple photomasks are needed. Together they create the foundation that allows a chip to perform millions of calculations every single second. Once the final photomask is complete, it's shipped off to a semiconductor fabrication plant. Here, cutting-edge lithography machines use the mask to print the delicate circuit patterns onto silicon wafers. The wafer is spun at incredible speeds, sometimes up to 5,000 revolutions per minute, to evenly spread a light-sensitive coating called photoresist across its surface. This ensures an ultra-thin, perfectly smooth layer for precise circuit printing. Next, a powerful laser beam passes through the photomask, projecting microscopic transistor patterns onto the wafer. The wafer is then treated with a developer solution that removes either the exposed or unexposed areas of the photoresist, depending on the design. Since chips require multiple layers, this step is repeated countless times, each one building upon the last, creating an intricate network of pathways and transistors. But printing the pattern is just the beginning. The wafer now undergoes etching, doping, and metal layering, steps that bring the design to life. Etching removes unwanted silicon, carving tiny trenches and holes where transistors and connections will sit. There are two main methods: wet etching, which uses chemicals, and dry etching, which relies on ionized gases for atomic-level precision. The next stage is doping or ion implantation, where high-energy ion beams inject elements like boron or phosphorus into the silicon. This changes its electrical properties, turning it into a true semiconductor capable of switching and amplifying signals. Insulating materials are then added to separate the layers, followed by metal deposition. Using copper or aluminum, ultra-thin conductive layers are formed through sputtering or electroplating, creating the high-speed highways that connect millions of transistors. After these steps, the wafer surface must be perfectly flat. A process called chemical-mechanical planarization polishes the surface to a flawless finish, ensuring no defects disrupt performance. With the transistors and circuits now fully built, the chips undergo rigorous testing. They are pushed to their limits through thermal stress tests, power efficiency checks, and real-world simulations to ensure reliability under any condition. Once approved, the delicate microchips are packaged in protective casings made of plastic, ceramic, or metal. Modern packaging even includes 3D stacking, where multiple chips are layered on top of one another to boost performance while reducing power consumption. Finally, these chips are shipped to electronics manufacturers and integrated into the devices we use daily: smartphones, gaming consoles, self-driving cars, medical equipment, and even spacecraft. But microchips are only part of the story. To see their true potential, we need to look at the machines they power, like laptops. Have you ever wondered how a laptop, the portable computer you use every day, is built from start to finish? The history of laptops dates back to the 1980s. In 1981, the Osborne One became the world's first commercially available portable computer, though by today's standards it was bulky and limited. Soon after, companies like Compaq and IBM improved the design, making devices lighter and more efficient. By the 1990s, advancements such as lithium-ion batteries and LCD screens revolutionized laptops, making them thinner, lighter and far more practical. Iconic designs like IBM's ThinkPad became legendary during this era. Fast forward to the 2000s, and laptops underwent a dramatic transformation. Sleek models like Apple's MacBook Air redefined portability, while powerful machines like Alienware catered to gamers demanding high performance. Today, laptops are more than just tools for work, they're essential for entertainment, education, and innovation. But how are these machines actually built? It all starts with the motherboard, the central nervous system of the computer. The process begins with a printed circuit board, where a stencil layout is placed and solder paste is carefully applied. This paste serves as the foundation for connecting hundreds of electronic components. Automated cameras scan the board for accuracy before robotic arms spring into action. Within just 30 seconds, as many as 150 tiny components are placed precisely onto the board. The assembly then passes through a reflow oven, where the solder melts and solidifies, locking everything into place. Another inspection ensures no errors remain. Next comes the laptop's display. Technicians attach protective films to the LCD screen and carefully connect delicate cables to the motherboard. The screen is then framed with a bezel, which includes the webcam and microphone, combining durability with design. Once completed, the display is ready to be joined with the rest of the system. The lower half of the laptop houses critical components: the speakers, touchpad, keyboard, and of course the motherboard. Cooling systems, including fans and heatsinks, are added to prevent overheating, especially in gaming laptops. Memory modules, Wi-Fi and Bluetooth chips, SSD storage, and a powerful battery are installed one by one. Finally, the keyboard is fitted, with laser etching adding precise lettering to each key. Before reaching consumers, laptops undergo intense quality control. Automated tests check the display, cooling system, and overall functionality, while technicians manually test features like color accuracy and keyboard durability. Only after passing these tests do laptops move to the final stage, packaging. Each unit is cleaned, boxed with accessories like chargers, and prepared for worldwide shipping. Many factories now also integrate sustainable practices, such as using solar power to reduce carbon emissions during production, ensuring technology advances hand in hand with environmental responsibility. And just like that, from a bare circuit board to a sleek and powerful machine, the laptop is born. It's a process of precision, innovation, and relentless testing, all to ensure the device in your hands performs flawlessly. So, which laptop brand are you using right now, and how well does it serve you? Share your thoughts, and stay tuned for more fascinating insights into the technology that shapes our world.